Assalamu alaikum students. Welcome to this CSE 423 lecture series. Today we will discuss about projection. Now what is it? In computer graphics, when we render some 3D objects, we present it on our screen. Our screen is a flat 2D surface, but how do we display a 3D object on a flat 2D surface? The 3D object needs to be deformed or changed or transformed in such a way so that it nicely maps to some 2D coordinates of our 2D display. Yes, it is the purpose, it's a process of converting 3D to 2D. More generally, it is a type of transformation. We have seen translations, rotation, scaling. It's just like that. We apply this transformation to every vertices of a 3D object and get a set of coordinates that can be applied to the 2D display. It doesn't need to be from 3D to 2D. It can be from any higher dimension to a lower dimension. We are basically lowering our dimension count. So 2D to 1D is also applicable, but most commonly we do 3D to 2D. Before we go any further, let's get familiarized with some terms we will use throughout this chapter. Since it is a type of projection, it needs some input points. These points belong to an object. There can be many subject points or target points of an object. We label them as P individually. So it can be P1, P2, P3, whatever. Our output will be a transform point called P prime. This is the projected version of our input point P. The process of projection basically emulates light rays. The rays responsible for projection are called projectors. They emerge from the object and goes towards the viewer. In some cases, we also consider that the projector rays goes from the viewer to the object, but both cases are totally valid. Now there will be an imaginary plane called the projection plane, which the projectors will intersect on their way. Every projected point P prime belongs on this plane. Since all projected points from the final rendered 2D image, this plane is called the view plane. So this view plane called every P prime in existence, since we are mapping the P points to P prime. And this image, this view plane actually maps to our display. In case of perspective projection, which we will look into soon, the projectors converge into or from at a single point. We call this point the center of projection or COP. This is essentially the viewer's eye or camera. In the case of parallel projection, which we'll also look into soon, there are no COP, but there is a direction at which the rays head towards. This is the direction of projection or DOP. This diagram will make everything clear. We have an object. Its image appears on the projection plane as the projection rays or projectors are intersecting it on a guided path. So this is the plane and this is the image of this object. So it is a flat 2D image and this object is a 3D object. The vertices on the cube, this object is a cube, can be labeled as P. So every vertex can be labeled as P1, P2, P3, whatever. The vertices of the cube's image on this plane can be labeled as P prime. So the vertices, each vertex is mapped to this plane as P prime. So it will be P prime 1, P prime 2, P prime 3, whatever. The projectors are shown as dotted lines here. And here, there's a point called COP or center of projection. Since this is a specific diagram of perspective projection, there could have been a distant direction of projection instead if it was a parallel projection. In this chapter, we are dealing with planar projection, where we project onto a flat plane instead of a curved surface. So there is a curvature projection, but we are not dealing with this in our course. There are two major branches of projections, which one is perspective and another one is parallel. Perspective projection can be further divided into 1 point, 2 point, or 3 point projections. Parallel projections has its own subcategories. If our projectors are parallel, we are viewing the object from an axis. We are basically doing orthographic projection. So orthographic projection means we are looking at an object from only one direction or from an axis, basically. Oblique is when we are viewing the object from a certain angle. So orthographic means we are viewing the object from either x-axis, y-axis, or z-axis. But in oblique projection, we are also viewing that object with parallel rays, but we are viewing with some kind of angle. And each projections have their own unique use cases. Here are some illustrations showing different types of projection. The first one is a perspective projection. So you can see the COP here. The other three are different kind of parallel projections. Notice for the parallel projections, the rays are not intersecting, but they are traveling in parallel. In case of this orthographic projection, which is a type of parallel projection, you notice we can only see one face of the cube. but in the other cases, we can see multiple faces. Here are few differences between the two major branches, which is perspective and parallel. These are few differences, but throughout this chapter, you will discover even more differences. We have already discussed some of them in just recently, so we will see them. But one new thing to notice is foreshortening here. What is foreshortening? It is a phenomenon of far away objects appearing smaller than near ones. So if you see buildings that are far away, we see as small. The sun is very large, but since it is very far away, it appears very small. This happens in perspective projection only, and it is more realistic since human vision itself is perspective, and this one is natural. Whereas in parallel projection, it doesn't support foreshortening, so the images appear quite odd and unrealistic. In case of parallel lines on objects remain parallel, which won't necessarily happen for perspective projection. Let's focus on perspective projection for now. We have already talked about foreshortening. Notice how the faraway trees appear smaller. We are familiar with that already. I have also said that in this kind of projection, the parallel lines on an object won't necessarily remain parallel. Like these rail tracks are parallel in reality, but in this image, look, they seem to converge into distance. They seem to converge into a distance in a certain point, a single point. This point is called the vanishing point. And by the way, don't confuse vanishing point with the center of projections. These are two different things. Every set of parallel lines have their own vanishing point. For example, we usually talk about 1 point, 2 point, or 3 point perspective projection. These figures correspond to the number of vanishing points present. Thus, the number of sets of geometric parallel lines supported. In reality, there are infinite orientations of parallel lines possible. So there can be infinite number of vanishing points also. So not just up to 3. Professional artists use this technique to draw complex orientations regularly. Perspective projection is used majorly in 3D games, 3D animation, and most importantly in VR. Here is a diagram showing the 1 point, 2 point, and 3 point system. A cube can have up to 3 sets of parallel lines. In the 1 point perspective projection, these two parallel lines seem to converge. So these two parallel lines on the cube seems to converge into distance, but these two, this one and this one, don't seem to converge. In the 2 point perspective, these pair of lines and these pair of lines seem to converge, but the vertical lines here, they don't seem to converge. In the 3 point system, we see every set of parallel lines all seem to converge at certain points. So these two parallel lines converge here, these two parallel lines converge here, and these two vertical lines also converge here. One thing is clear: perspective projection doesn't preserve parallel lines. It rather try to converge or divert them. So it's definitely not an affine transformation. When we analyze or derive formulas for projection, we usually simplify the process in a 2D diagram to make it easier. If an object is defined by AB, their projected image will appear on the projection plane. So the projection plane is in the middle here, as their projected image will be A prime and B prime. The projection plane itself is usually a plane parallel to the XY plane, or it could be the XY plane itself. The x-axis, it's not the x-axis, it's actually the z-axis. The z-axis intersects the plane. The intersection point is regarded as the projection plane. So this blue line is actually the z-axis. On the left, the z value increases. So this one is towards the positive z, and towards the right, the z value decreases. We usually put the plane in the middle of the setup, as said earlier, and put the object or the subject on the right and the viewer on the left. So in this, this is a perspective projection diagram. So the viewer is here on the COP point. In case of parallel projection, there might be the distance of direction of projection instead. Let's move our focus to parallel projection for now. In this case, the parallel lines on the object remain parallel in the projection as well. So these two green railings here, in reality, they are actually parallel. And also in our projected image here, we can see these are still parallel. Since the rays are parallel, they won't converge. So we do not have to have any COP here. Or in other words, the COP is at infinity. The rays, however, do have a common direction. So we rather have a direction of projection or DOP. And no convergence means no foreshortening. So the projected image looks less realistic. But even though it looks less realistic, the parallel projection is good for architectural designing because it gives an accurate sense of measurement. And some games also use parallel projection, like the game Clash of Clans, Age of Empires use isometric projection, which is a type of parallel projection. These are several types of parallel projection applied to the same object, a desk. On the top part, we can see various orthographic projection. So top view, front view, side view. We can see only one side of the desk at a time. On the bottom part, you can see oblique type of parallel projection. So cabinet and cabinet are very similar, just their scaling and angle are different. Cabinet projection actually comes from furniture design, and a desk is also a furniture. Whatever type of parallel projection it is, the projectors are always parallel. But in case of orthographic, the rays are perpendicular to the projection plane, or in other words, they match with the normal vector of the plane. The 2D image of the 3D object will appear as it is in 3D, but flattened. We already know what is a normal vector. It is basically a perpendicular vector to a certain surface. In this case, our surface is a plane, our projection plane. In case of oblique type, the rays aren't aligned with the plane's normal vector. They are rather inclined in an angle, which makes the direction of projection tilted. For this reason, the projected image a bit shifted. So this is the projected image. It appears a bit shifted from our original object. In our transformation chapter, if you have gone through it already, we already did several types of transformations like translation, scaling, rotation, etc. using some matrices. Here in this chapter, be it parallel or perspective, we also do some matrix steps because planar projection is also a type of linear transformation. We have a matrix. We multiply that matrix by the homogeneous version of our input point as a column vector x, y, z, and 1 in homogeneous coordinates. After multiplying, we get another column vector as expected. So this is our matrix. X, y, z, 1 is our point as a column vector. And if we multiply these two, we'll get this result. But this isn't our final answer. Since a lot of projections aren't affine transformation, the fourth value, known as W, won't necessarily be 1. So in our transformation chapter, we saw this W value always appearing 1, but in this chapter, we won't necessarily see this value to be 1. It could be anything other than 1. In this case, we need to divide all 4 values by W to get our intended result, so that our resulting W becomes 1, and we have successfully removed the W term from each of these components. Without this step, our projection calculation is incomplete. So this is important. Don't miss this and remember this. This process is called perspective division. Now we will derive the actual projection matrices. First, we will look into parallel projection. We know there is no COP here, but only a direction. This direction is controlled by some angle parameters and or scaling factors. So cabinet, cavalier, orthogonal projection, have their own set of value for these parameters. To derive, let's analyze this diagram. Here the projection place is basically the XY plane. Only a portion is shown here, not the full thing. It means the plane goes through the origin. And every point that is on the plane will share the same Z value. Origin Z value is 0. So all points on this plane will have their Z value to be 0. With deriving parallel projection, we will derive only for oblique projection, since orthographic projection is just a special case of oblique projection. Our target point P is here in magenta color here, and our P prime point is this orange dot, which is our projected point. Since P prime is on the plane, its Z value called Z prime must be 0. Now how to calculate X prime and Y prime? We know for oblique, the projected image appear a bit shifted. This is due to some offsets being added to the X and Y values. So if we go a little back, for oblique projection, this was our object and this was our object's projected image. It appears a bit shifted or tilted. Now, how to calculate these offsets for X and Y? First, we consider a point equivalent. So this black point here to our target point P, but on this plane. So this black point is actually residing on this plane. Since every Z value on this plane is 0, this point's Z value is also 0, but its X value and Y value is same as the X value and Y value of our target point P. We connect this black dot and this our target point P with a dashed line here, black line. This line is perpendicular to this plane. Now for the offset. To calculate them, we are using a combination of this lambda and beta. So this is a lambda line here, line segment actually, and there's a beta angle here. This beta makes an angle with the x-axis or horizontal axis. More specifically, it's an inclination angle making angle with our x positive direction. This is a solid input parameter, which means it must be known to build the matrix. This beta can go on full circles. So this beta has a range of 0 to 360 degrees. Or if we're using radians, it means 0 to 2 pi. We simply apply the strategy of converting polar coordinate to Cartesian. So we have converted this thing in school, converting r theta to xy. Considering the lambda value like r and the beta like theta, it will give us two components, a lambda cos beta on the horizontal axis and lambda sine beta on the vertical axis. These are actually our offsets for x and y respectively. Adding them to the x and y values, so this x and y values in this black dot, if we add them individually to individual components x and y respectively, it will give our x prime and y prime. So we have got to know the z prime from earlier, and we now know the x prime and y prime. So this, using this formula, we can derive the value of x prime and y prime. All right, but how did we get lambda? What is lambda? We know that beta is an inclination angle, but what about lambda? Lambda is basically a factor that scales the object depth axis or z axis. So it will scale this object. So it's just a point here, but if it was a cube here, we can easily see it does scaling on that object on the z axis. If you also notice this orange line here, this orange line connected by p and p prime, this is actually our projection ray or projector. If we make a triangle from this black dotted black dashed line, this lambda line here, and this orange line here, notice this black dashed line is perpendicular to our plane. We will get a right triangle. So this right triangle here, we can see, so this lambda corresponds to this lambda. This orange line is this orange line here, and this black dashed line is this black dashed line. So this is a right triangle. By the way, this black, as I said, this black line is perpendicular, and the height of this triangle is this black line, which is delta z. This delta z is basically the distance between our target point and this projection plane. So in our projection plane, the z value is 0. On the target point, the z value is z. So the value of the delta z is essentially z minus 0, which is just z. All right, we can now call this internal angle between the projectors. So this internal angle here, we can call this alpha. This alpha angle is basically the angle of skewness. So this angle is between this projection plane and our projector line. So this projection plane is here. We cannot see here because of 2D representation. And our projector line is this orange line. The angle between them is alpha. Just applying simple trigonometry, we get this tan alpha ratio. As I said earlier, alpha is the angle of skewness. This actually controls how slanted that object will be projected. We just rearrange it and get a term from lambda. So lambda equals to delta z by tan alpha, and we already know delta z is equals to just z. We now substitute this equation into the formulas for x prime and y prime. So if we put the lambda term, substitute it here for these two equations, x prime and y prime, we'll get these two equations. So x prime equals to x plus this thing, and y prime is similar, but with the sign beta. And we already know z prime is equal to 0, since the projected point is on the projection plane, and the projection plane is actually the xy plane. Now, but on the right, I have written these same equations as a second time, but with the coefficients color coded. So the x term coefficients are color coded as red, the y term coefficients are color coded as green, the z term coefficients are color coded as blue, and the leftover part is color coded as purple. Since there are no leftover term here, we cannot have any purple term here. But how can we build such matrix from these three equations? If we have a set of 4 equations like this, we can build the matrix from the coefficients, but we only have 3 equations, x prime, y prime, and z prime. But what about w here? So we don't know w. Since we are doing parallel projection here, where parallel lines remain parallel, we can set w to be 1, just like we do for affine transformation. We set the w to be 1, we do the same here. So terms like x prime into w will just be x prime. Since w is 1, it will just convert into x prime, y prime into w will just be y prime, and same for z prime. Since w equals to 1, we can consider this one also as an equation of its own. Now we have 4 equations. Now we can apply this strategy from here and just place the coefficients into our 4 by 4 matrix. So what we are doing here, we have our matrix. We have just put the coefficients here in their respective places. We are multiplying this matrix with our point, which is mounted as a column vector in our homogeneous coordinate system, and multiplying this will give this column vector as well. So this column vector will contain x prime into w. So every component multiplied w, and that is w itself. But since w is 1 only for this scenario, we can just write like this: x prime, y prime, z prime, and 1. By the way, this w equals to 1 is only applicable for this term, this specific scenario. It doesn't apply to other terms like perspective projection. Let's head a bit back. If we consider the distance between P and the projection plane, which is delta z, to be 1, we can use the lambda as the scaling factor by itself. Usually, we consider delta z to be 1. So we then get this relation, which is tan alpha equals to 1 by lambda. So we are just substituting delta z by 1, and we can just rearrange it to be lambda equals to 1 by tan alpha or cot alpha. This is an alternate version of the same matrix we just derived, but with lambda instead of tan alpha. We just replace the 1 by tan alpha with lambda because we got this relation. To perform the maths, we either need to know the combination of alpha and beta, or the combination of lambda and beta, since we just got to know this conversion formula here. This parameter ultimately controls the direction of projection or DOP. So for different types of oblique parallel projections, there are different combinations of this alpha or lambda value. The beta value can be anything between 0 and 360 for all causes. Alpha or lambda control the skewness and scaling factor, and each types of parallel projection have their own configuration. For cabinet projection, we can supply the scaling factor to be half, or the skewing angle to be 63.4. For cavalier, scaling factor is 1, and the skewing angle or alpha is 45 degrees. Orthographic projection is a special case of oblique projection where the skewing angle is 90 degrees. If we apply the alpha to be 90 degrees, it will make the direction of projection perpendicular to the projection plane. And we can only see one side of this cube width. So in this orthographic projection, we can only see one side, whereas in these two cases, we can see multiple faces. Let's see a simple example. We need to apply cavalier projection to a point called 10, 20, minus 40. So this is our P point. Since it is cavalier, the alpha angle will be 45 degrees. So for cavalier, the alpha angle will be 45 degrees. And the inclination or orientation angle is given as beta. Here is 30 degrees. So alpha is 45 degrees and beta is 30 degrees. So we already know the combination of alpha and beta. So we can apply this formula of building our matrix. So if we put the alpha and beta values in this formula, we will get this matrix here. So this is our final projection matrix for cavalier projection. We multiply this matrix with our point. So we mount this point as an homogeneous coordinate column vector and put 1 here. Now after multiplication, we will get this column vector. So minus 24.64, and this is 0, 0, and 1. And since we have already got 1 in the W term, we don't need to do further division. We can just keep as it is. So our P prime point, or the projected point, is minus 24.64, 0, 0. As said earlier, in case of orthographic projection, the alpha value will be 90 degrees. That means, in this case, the tan alpha term will go to infinity, and since it is in the denominator, these two terms, so these two blue terms here with the cosine and sine terms, these two terms will go to 0. So in case of orthographic projection, we just replace these two terms with 0. So that means in case of orthographic projection, the matrix will be like this. So it's like kind of resembles our identity matrix, but this term here is 0. See, this one is a constant matrix. So if we projected a 3D point called with coordinates d, e, f with orthographic projections, we'll end up with the projected point d, e, 0. So we multiply this orthographic projection matrix with our intended point, and we will get just like in the input. So d maps to d, e maps to e, but f maps to f. What is it? The x value will map to its original x value. The y value will map to its original y value, and the z value will map to 0. So the z part will always be 0. So it's basically mapping a 3D point down into a 2D point where the z value is 0. This puts an end to the projection chapter introduction. We will discover more projection stuffs in upcoming lectures. Till then, take care. Goodbye. Assalamu alaikum.